Hello, everybody. Hello. Hello. It's time to stop talking and start listening. You're all invited, by the way, to Pi Day afterwards, which is at 2 o'clock. However, those not in some sort of costume will be at the end of the line. I want you to know that. So, this is Welcome to Munch and Learn. This afternoon we have Dr. Stephen Sommers, as you can see, and there is someone else who will be introducing him, so just welcome.
Hello, I'm Kelsey Wilkes, and I do the data entry for NASCA. And I'm thrilled to be here and also to look out there and see lots of people I know from other parts of my life in Prescott, which is lovely. So thank you, Rudy, and thank you, Tricia, who's somewhere in the back. Wave, Tricia. So thank you for being here, and we also thank you for a partnership opportunity with Yavapai College and Ollie and your Lunch and Learn event. Want to just tell you that NASCA is a nonprofit 501c3 organization. We're nonpartisan. We have non-electoral grassroots. So we are out there because we care about climate. We strive to invite and inspire people to step up, take action through education and empowerment in addressing climate change and its impact on the local, state, and national level. For more information, we do have a website which you can check, and there's lots of information as you leave. You can also sign our white petition. So we have over 900 petitioners in northern Arizona who are going to be asking our federal legislators to step up and save the climate. You can also make donations. There will be a donation jar going around. We need money to do advertising and things like that. And we also love people to volunteer. If you didn't sign in, we'll just pass around this blue sheet. And if you'd like to jump in and help volunteer, there's a spot to put a nice V for volunteer. So I'm going to move ahead and introduce Dr. Sommer. He is the Director of Education at the Miriam Powell Center for Environmental Research at Northern Arizona University. His doctoral work is in ecology, sustainability, and he has studied effective communication across all cultural boundaries in many contexts, including a PBS film production. And he's now going to talk to us about climate change and its effects. So, Dr. Sommer, thank you.
Thank you, Kelsey. No need to clap yet. You don't know if this is going to be any good. So, hope y'all are doing well this afternoon. We will, as Carrie and Kelsey have been saying, we're going to be talking about climate change. It is the challenge of our time. It's something that we all need to pay all the attention we possibly can to. And what I'm going to try to do today, this is really the Climate Change 101. We're going to talk about what we know about climate change and some of the consequences that we're already seeing, and a little bit about consequences that might be coming. When I first put this together, I had climate change causes and cascading consequences, and then I realized, no, it's really cause and cascading consequences, and I'll show you how we know that. So before we really get going into climate change, I would just like y'all to meditate for a moment on how you know the things that you know. We are a very social species. Let me see, this is not working. Battery's good? It did, yeah. Well, here's this. That's not going either. The whole thing's frozen. Let's see if it'll work from there. Yeah, okay. So the way that we know things, generally speaking, we're a very social species, right? So we learn from each other. Many of the things we know, we learn from our families to begin with, then school, now media. We also learn, for many people, faith is a very, very important way of understanding things. We do observation as well, and if we have a really good education, a basis for understanding what we're observing, then we can also apply reasoning to come to conclusions about how the world works around us. But it's getting harder and harder to trust the sources of information in this day of what is now being called fake news, what we used to call propaganda. And so in this environment, how do you know when somebody's telling you something, whether it's really true, whether it's something you should bring into your understanding of the world, or say, wait a second. And for me as a scientist, I would say we really need to start doing things in a more evidence-based, critical thinking kind of way. So for the scientific community, it's about data. And we argue with each other all the time about what is the strongest data, what is the right analysis of that data. And so within the scientific community, we're constantly comparing and arguing about what's the best use of this information or that. So if we can do that in our culture in a more thorough way, I think we can get past some of this fake news and propaganda issue. And I'm sure you all have seen a lot about climate change. You all have heard about climate change, I'm sure? Yes. And year after year, we see headlines like this. You know, the 11 warmest years on record have been in the last 13 years. This is the warmest year on record, and so forth. So we hear a lot, but we don't want to just go off the headlines either. Because the headlines also can include things like this. We are way past the time when we can have totally out of touch leadership who do not understand what the scientific community has been saying about climate change for 30 years, really for over 100 years. And then you can see reports like this too. The World Bank just came out last year with Groundswell, which is an overall analysis of how climate change is affecting populations around the world and how that is expected to translate into additional climate refugees beyond the other kinds of things that are causing people to flee their homes. And if we're working right now, this is actually the first in a 3-part series. This one is the basics. Then we'll talk about climate refugees and Arizona's future. In the second one, we don't have it scheduled yet for Prescott, but we're hoping to. And then the final one will be climate change building a path forward, where we'll look at the various studies of how people are projecting a way to get past our current crisis. And for some folks, it's hard to process through a lot of data. So a visual can, I think, make a really big difference. And this is an easy one to grasp. For many years now, we've seen a retreat in the extent of Arctic sea ice. And this is just a graphical depiction of that. Oh, hit the wrong thing. And so Arctic sea ice, as well as the glacial cover of Greenland and Antarctica, have all been retreating. And it's not just one part of the world, it's every part of the world. Glaciers have been retreating, and that's in keeping with what's been going on with the average global temperature. So I'm going to couch these climate change basics in terms of what do you say to your Uncle Bob? I'm used to talking to younger audiences at the university. So maybe, we'll not say Uncle Bob, let's say neighbor Bob. What do you say to your neighbor Bob when he says climate change is a hoax perpetrated by China? Well, what do you say? What do you say when neighbor Bob says, but climate has always been changing, so what? Or, yeah, climate is changing, but it's not caused by human beings. So I'm going to give you solid answers for all of these things, and I want you all to become emissaries to the neighbor Bobs of the world and take this information with you, because we need to get everybody in on this conversation if we really want to do anything significant about it. I don't know if y'all remember from a few years back, but this Coca-Cola ad campaign about the polar bears just having a great time drinking Coke up in the Arctic. And of course, the reality for polar bears up in the Arctic is quite different. They're not drinking Coke. In fact, they're drowning because they're now having to swim such large distances between the smaller and smaller chunks of ice floe where they are adapted to make a living hunting seals, and they're just not in good shape. Many of them are drowning because they cannot get to the places they need to be. Some of them are moving to shorelines, and they may have a chance of restructuring their adaptation to the shores, but it's not their ideal habitat. Okay, how many of y'all have heard of the greenhouse effect? Everybody, I hope. And it was first proposed by Joseph Fourier in 1824. So this is, again, it's not a new idea. And nor is the greenhouse effect a bad thing. In fact, without the greenhouse effect, life on Earth as we know it would not be possible. And the way it works is we get lots of different wavelengths of radiation from the sun. Some of that is reflected and refracted before it reaches the Earth's surface. Some of it's absorbed by the atmosphere, but much of it reaches the Earth's surface. And when it's absorbed by a physical object, that physical object heats up. Warmer objects re-radiate, on average, towards colder objects. So as the Earth's surface warms up, much of that heat energy is re-radiated back towards outer space, shifted towards the longer wavelengths, infrared radiation or thermal radiation. I'm sure y'all have heard of that as well. And those longer wavelengths go back out towards outer space where it's cooler, but many of them are absorbed by greenhouse gases, because we call them greenhouse gases because they absorb those wavelengths of thermal radiation. And it's just like at night. When you're on a cold night, you are radiating thermal energy to all the colder objects in the room, and you put on a blanket so that less of that radiation leaves you and more of it stays in. Well, the greenhouse gases are a blanket, and they keep that thermal heat energy in. The thicker we make that blanket by adding more greenhouse gases, the more of that heat we keep in. And that's really what we're doing. So the greenhouse effect is a good thing, but we're changing the strength of that greenhouse gas by thickening the blanket or the greenhouse gas concentration in the atmosphere. Okay. And we can look at this in a variety of different ways. One way is to look at our neighbors, Venus and Mars, and to start getting you to understand what's going on here. We call the Earth's atmospheric pressure 1 atmosphere of pressure at sea level. Ground level on Venus, they have a much denser atmosphere that is 90 times as dense as ours. So we call that amount of pressure at the surface 90 atmospheres. And Earth has a very thin atmosphere, Mars has a very thin atmosphere that is only 0.007 as dense as the Earth's atmosphere. In both of these cases, though, they have high concentrations of CO2 in their atmosphere, over 95%. And so we can look at the relative strength of the greenhouse gases there compared to Earth. On Earth, without the greenhouse effect, our average temperature would be minus 18 degrees centigrade. And most water would be frozen most of the time, and life as we know it would not be possible. Because we have a greenhouse effect, our actual average temperature is plus 15 centigrade degrees, and that's an overall greenhouse effect of plus 33 centigrade degrees. That's in spite of the fact that we have a very low concentration of CO2 in our atmosphere. 0.03% of our atmosphere is CO2. For these guys, they've got a dense atmosphere and most of it is CO2, so they have a very, very strong greenhouse effect of plus 523 centigrade degrees. For Mars, they've got high CO2 concentration, but very thin atmosphere. So their overall greenhouse effect is only plus 10 centigrade degrees. Okay. So because of all of this, life on Earth is possible in the way that we know it because life is adapted to having liquid water, having seasons, all the different things that we have here that are the way they are in part because of the greenhouse effect. Okay. So another way we look at this relationship between CO2 concentration and Earth's average temperature is by looking back through time, geological time, by taking ice cores in places like Antarctica, where there's a very, very deep deposition of ice. We can take deep cores, and if you think about that ice, year after year, snow is deposited in Antarctica. It gets compressed, becomes ice, another layer of ice. So the top layers are the youngest, and as you go deeper, each successive layer is older. And you can look at the little bubbles in that ice, which are a representation of what was the atmospheric composition at the time that that ice froze. And with that, we can take bubbles from these different layers and get an idea of what the CO2 concentration was back through time. We can also look at the water composition, and this is a little more complicated, but y'all have heard of heavy water? Some of you maybe. Heavy water is water that has heavier isotopes of either hydrogen or oxygen. And the way in which global temperature affects heavy water relative to normal weight water is that it takes, just because it's heavier, it takes a little bit more energy to evaporate the heavy water. So when the temperature of the ocean surface is higher, relatively more of the heavy water is evaporated. And so the relative proportions of heavy and normal weight water in that ice give you a record of what the average temperature of the ocean's surface was at the time that that moisture evaporated to become snow on Antarctica. Okay? So in these ice layers, we've got both a temperature record and a CO2 concentration record. One of the more famous, well-known data sets is from the Vostok station, where they have cored 3.6 kilometers down through the ice, which goes back about 420,000 years. So we've got a long record in that ice core, and I'm going to show you some of the CO2 and temperature data, not for the whole thing, but for the last 160,000 years. So from the present back to 160,000 years ago, this is the CO2 concentration from those ice bubbles and the Earth's temperature from those heavy water, normal water ratios. And what can we see? We can see that there's a pretty good correspondence between CO2 concentration and temperature. CO2 concentration goes up, temperature goes up. As CO2 concentration comes down, temperatures have been coming down. Back up, back up. Okay? So based on this kind of record, we also see that there's a pretty high correspondence, not a perfect correlation, but a pretty high correspondence between CO2 and Earth's average temperature. Is everybody following me on all of this? If I'm saying anything that's Greek to you or that you have a comment about or a question, please raise your hand. Let's make this as much of a discussion as possible. I know there are a lot of us in the room, but the more we can make it a discussion, I think the better it will be for everybody. Yes, question.
So why was it so high, 140,000?
Right in here. Good question. So the question is, why was the CO2 so high 140, 100 to 120,000 years ago? I believe that was triggered by an increase in volcanic activity, but there were probably a number of different factors that were triggered by that. So it wasn't just volcanic activity either. But yeah, so CO2 has gone up and down in the past across this kind of range from 180 parts per million to as high as 280 parts per million, which is where we were also most recently. And I'll show you some data on that in just a moment. And here's just for the last 1,700 years, how the temperature of the Earth, the average temperature of the Earth has changed. And the way they often show these is they take the long-term average and call that 0, and then they refer to rises above that long-term average as high anomalies from that average or low anomalies from that average. And you'll see a lot of graphs that I show you that are like this, where 0 is the long-term average. And across that time period, you can see that we've had some relatively warmer and relatively cooler time periods, and that right now, what we're seeing is outside of the range of temperatures that we've seen for the last 1,700 years, and that the rise has been very, very rapid. And here's more recent, what we've been doing. So pre-industrial revolution, we were at about 280 parts per million. As of today, we're at 409 parts per million. And if anybody's interested in tracking these numbers, all you have to do is plug into Google NOAA, N-O-A-A, CO2, and you'll get the record. These are records from the top of Mauna Loa, out in the middle of the Pacific on Hawaii. And you can see from 1960 up through the present, there's been a dramatic rise in CO2, let alone the rise previous to that, starting in 1880. Yes, question?
Just a second. Has the volcanic activity grown up from 1960 to 2020?
Good question. So yeah, that's always the question, is how much of this is natural versus how much is human caused? And we'll get into that more as we go along. But yeah, no, this CO2 rise is not due to volcanic activity. So it's a pretty dramatic rise. And anybody, what's this little red cycle? Anybody have any idea? It's seasonal variation. Very good. And how would seasons affect CO2 concentration? Very good. Plants grow in the northern hemisphere and they take up carbon dioxide. Yes, so the process of photosynthesis takes in CO2 as a raw material, combines it with water and sunlight energy to produce chemically stored energy like carbohydrates. And so photosynthesis, when photosynthesis is highest in the summer, they would be taking up lots of CO2, and those would be the troughs in this cycle, summertime, when photosynthesis is most active. But what else do we do with that chemical energy, those carbohydrates? Well, there's that, but we'll get to that a little bit later. For right now, just what's this natural annual cycle? We eat carbohydrates. We're about to eat some pie, I understand. And when we do that, we burn those carbohydrates physiologically, breathe in oxygen, and what do we breathe out? CO2. So we burn those carbohydrates, that chemical energy, and produce CO2. So that's respiration. So photosynthesis takes in CO2, respiration puts out CO2. So the peaks here in that red oscillation are winter, when there's relatively more respiration and less photosynthesis. Okay? And if you think about that, that's how much change all the living systems in the northern hemisphere have an effect on overall CO2 concentration. So for me as a biologist, that's a massive change in CO2 from there to there. And so for me, this amount of change is tremendous. Yes?
You're talking about the northern hemisphere. The southern hemisphere is just the opposite.
Exactly,
So
yes.
how does that work into your
Excellent question. So yes, so the opposite is happening in the southern hemisphere. Why are we seeing this regular oscillation? Well, it's largely because there's not much mixing between the northern hemisphere atmosphere and the southern hemisphere atmosphere due to the way circulation happens at the equator. There's a little bit of mixing, but not much. Enough so that even though Hawaii isn't so far from the equator, it's really reflecting what's going on just in the northern hemisphere and not what's going on in the southern hemisphere. Well, this rise is, but this oscillation, not so much. That's the whole natural balance of the relative rates of photosynthesis and respiration for all living things in the northern hemisphere. Question?
Does the increase in CO2 correspond to the estimated burning of fossil fuels?
This here, that rise, yes. And I'll show you in a few minutes some data on that.
Thank you.
Yeah, they use a number of different methods, and economics is one of them, but they know how much fossil fuels have been mined or pumped, as it were, and processed and distributed. So that's one of the main ways that they estimate how much fossil fuels are burned. Yes, question.
Hi, how much does the increase in population, which went from 1960 to today, how much does that have on the CO2 influence? How much influence does it have?
So what is the effect of growing human population on all of this? I think y'all can imagine that it's pretty directly related. So each of us has a carbon footprint due to use of fossil fuels, the kinds of foods we choose to eat, and all the different things. And even if each of us was having the smallest possible carbon footprint that we can manage within the way we live, you multiply that small carbon footprint by 7.6 billion, and you still have a very large carbon footprint. So underlyingly, population is behind all of this, but still within the choices we make in our lifestyles and what we do, we can have either a large carbon footprint or a small carbon footprint. We get into that more when we talk about building a path forward. Where can we reduce our carbon footprints? But population is the key driver under all of this. Okay, so for a biologist, this amount of change is dramatic, and this is just since 1960. So this amount of change from 280 to 409 parts per million is a very significant change. And here is what I've been telling you about. So photosynthesis takes in CO2 as a raw material, combines it with water and sunlight energy to produce carbohydrates and other kinds of chemical energy. And then the plants they respire themselves. They use some of that chemical energy, and we call all of the photosynthetic product gross primary productivity. And then once plants have used some of it, the remainder is net primary productivity. And that's all of the chemical energy that's available for animals on Earth. Then respiration does the opposite. It takes that chemical energy, combines it with oxygen, burns it basically in a physiological way, releases CO2 and energy, which we use to power our lives.
Excuse me, I have a question.
Yes, question.
Yeah, I actually went back to the former slide. We're at 409 parts per million of CO2 now, and it was 280 in 1880.
Yes.
Is there an ideal, and is there a tipping point that's been determined?
Yeah, so the 280 was the natural level due to all the different natural processes that affect CO2. I think that kept the Earth in pretty good balance. So if you want to define an ideal, I would define it as that. Whether there's a tipping point is harder to really say. But recent reports from the Intergovernmental Panel on Climate Change suggest that we've already risen by a little over 1 degree centigrade since the time when we were back at 280. And they're saying we should avoid 1.5 degrees centigrade warming. And so a lot of the discussion now is about how do we avoid 1.5 degrees centigrade warming. I don't know that there's a step function in terms of, when does this all dramatically change, but there are some things that we anticipate will change dramatically, like as the permafrost melts, and it's already melting. There's a lot of carbon in that permafrost material. If you degrade that carbon when it's saturated with water, you're basically going to degrade it under anaerobic conditions because there's not so much, the oxygen can't get in through the water that quickly. And when you do that, then you produce methane instead of CO2. And if we release huge amounts of methane because permafrost starts degrading, that could greatly exacerbate the whole climate change issue. Because methane is a much stronger greenhouse gas than CO2 on a gram per gram basis. So the reason we talk about CO2 all the time and less about methane is simply because CO2 is the main greenhouse gas that we're affecting in the biggest volume. Our effect on methane has been relatively small. But if we change things to where natural systems start producing lots of methane, that could become a step function, kind of a major turning point. Yes, question?
You were talking about the permafrost melting. Could there be things like viruses that would then be released that would also harm people and animals?
I guess that's possible. Certainly there are diseases of the past that have reemerged as we've unfrozen carcasses from ice and different things. But so far, none of those have really become massive diseases for human beings. And I don't know how much potential there is for that. I think if you look at the potential for disease, the main issue there is human population, because if you look at the evolutionary models for disease, host density is the biggest factor affecting the rate of evolution for parasites. Okay, so as our population gets larger and larger, the potential for spread and evolution of our disease organisms increases along with that. So I would worry less about that coming from the permafrost and more about what's going on because of human density changes. Yes, Dory.
Human population growth as well as animal population growth, methane abatement, isn't that also shown on this part as well?
Not.
That we grow for food.
Yes.
Stephen, can you repeat that question so everybody can hear it?
So the question is, would this also reflect increasing methane? Because we're growing animals for food. This doesn't. This is actually a direct measure of CO2, but there would be a related rise in methane. It would be a much lower curve because we're producing less of that, but there's been an increase in the production of methane through the way we raise animals and several other different processes. Yes. But this is all about CO2. This graph is about CO2. Yes.
I have a comment getting back to the permafrost and its melting. Yes. And germs that have been extinct for a long time actually coming to life. And I think one of the aspects of our population growth and forced migration, our diets, are all decreasing our immunology, our individual immunology. And I think that if this does in fact occur, we're going to be more susceptible to these germs?
That's a good point, and it's certainly a possibility because we have antibiotics and so forth. Many individuals who wouldn't otherwise have survived have been able to survive, and so we've been weeding out weaker immune systems less than we would otherwise, I guess. So, there's what you're talking about is a possibility. How strong that is, I'm not really sure. But I've heard other people speculate about that. Question?
Hold on, Edna. Hold on.
Oh, thank you. Is 1960 as early as we started keeping track of the carbon dioxide?
On Mauna Loa, I think the records go back a little bit further for Mauna Loa, and certainly they go back further from other sources worldwide. We've been monitoring CO2 by instrument recordings for longer than 1960.
Saul, why don't you stand up? I'll see you.
Sure. I'm looking at the curve, and it's pretty linear. The question I have is this. Since the periodic changes, the red line is pretty constant all the way across from 60 to 2020, and yet the curve is going straight out almost to 30 degrees or more.
Yes.
What happened before 1960? What changed to make this get so steep?
You mean in terms of overall CO2 concentration?
Correct.
Well, we'll talk about that a little bit, but one of the main things, the reason we use the pre-industrial revolution's concentration of CO2 as a reference point is because it was really the Industrial Revolution and the massive use of fossil fuels that has caused this primary change. There are other things involved, but it is way more fossil fuel related than any other factor by orders of magnitude. I'll show you the data in just a second. Here it is, in fact. So if you look at this, these are from 2006 EPA records. Fossil fuel combustion was 5,637 teragrams of CO2. The next was non-energy use of fuels, which is also fossil fuels, iron and steel production, and many of these things. So if you look at them all, this one's about, 125, 130 something teragrams. The straight use of fossil fuels is over 5,600 teragrams. So there's almost no comparison between the use of fossil fuels as fuels and any other source of CO2. Yes?
Is the fossil fuel broken down into coal and oil?
Coal and oil and methane. We also mine methane, and yes.
The coal is generally used to produce electricity.
Yes.
The oil and gas are used for transportation.
Yes.
Do you have a breakdown as to how much of that 5 million whatever is gas and how much is coal?
What are the relative proportion? What are the relative contributions of gas and coal and various to this? Yes, those data exist. I don't have them here with me. Mainly for this, I wanted to make the point of what are our primary activities that are affecting this CO2 concentration and not break it down by different components of fossil fuels. But we can get into that in some of these later presentations where we'll talk about those in more detail. For right now, I want to look at this. One of the things that this particular listing does not include, and it doesn't include cement manufacture, so cement is actually another big source of CO2 in addition to fossil fuels, but there are also some other things. So all of these things, industry, residential, commercial, transport, and energy production are all fossil fuel types of things. But there are some land use things in here that are significant as well. So deforestation. You cut down a forest or burn down a forest, where does that CO2 end up? A lot of it in the atmosphere, either through the burning or through decomposition of that organic material. And so it's not just forestry, when we convert any natural ecosystem into a human ecosystem of some sort, whether it's an agro-ecosystem or a parking lot or whatever, there's a lot of carbon in that natural ecosystem that ends up being burned or degraded and then ends up in the atmosphere. It's not just forest and conversion of ecosystems, but also soils. Soils contain a lot of carbon. And when we till that soil every year, what are we doing? We're increasing the oxygen content of the soil, which increases the rate of decomposition of all that carbon. And so we've basically been mining our soils by tilling them year after year, releasing lots of carbon and washing out lots of nutrients. So agriculture and various kinds of land use are also a significant part of our CO2 footprint, but they're still small relative to the fossil fuel stuff.
Excuse me?
Yes, question.
Yes, on your slide before that, you had natural gas systems.
Yes.
And showing a lot smaller bar than the fossil fuel. So are you talking about natural gas combustion? Or are you just talking about something that occurs naturally?
No. That's natural gas combustion. Okay. Natural gas is a term for a type of fossil fuel. It's not a natural process.
Okay, so burning natural gas causes less CO2 than the oil and the coal?
Well, yes, but primarily I think because we're burning less of it. Not because it releases that much less per gram that we burn. I mean, it does release a little bit less per gram as well, but mostly this is because we're just burning less of it. Yes, question.
Interesting, when you look at your last chart, no, the one that has that one. If you took out the growth of energy, everything else is about the same. Nothing much changed. If you look at all those charts, they're basically uniform across. The reason they're going up is because energy is going up so high.
It is something that has grown more than many of the others, yes. Yeah. And so all of these things combined have now put us over 40 gigatons of CO2 emissions per year, which is, again, a very large amount. Okay, so now your uncle, neighbor, Bob, says, yeah, well, climate changes all the time, and the answer is yes, Bob, it does. And we know a lot about how it has changed. So let me show you, Bob. For the last 300 million years. So this is present in this first graph down to 300 million years ago. And here's how the Earth's average temperature has changed over that time across a 10-degree centigrade scale. So we've seen large changes in the Earth's average temperature in the past, looking like this over 300 million years. And this is due to the changes in the location of the continents, tectonic shifts. How would that affect it? Well, as the continents shift, it changes the circulation of the oceans. And the circulation of the oceans is how that incoming heat gets trapped and stored on Earth. So as we change the ocean circulation, it can change the overall Earth's average temperature by that much. Okay? So over 300 million years, we've seen this, and that has been due to tectonic shifts. And we call that one of the many natural forcing factors. If we take a look at the last 3 million years of those 300 million years and expand it out like this, then across about a 6-degree centigrade range of variation, we see this pattern. And those are all of the different changes in the Earth's orbit around the sun, the eccentricity of our orbit and the change in the tilt of the Earth's axis and all of those things combine. Each of those different things has its own cycle of change, and combined they give you a pattern that looks like this, and we refer to that pattern as the Milankovitch cycles. Some of you may have heard that term before. And so all of these changes are due to another set of natural forcing factors, namely orbital changes. If we look then at the last 50,000 years across which the Earth's temperature has warmed like this, and expand that out, again across about a 6-degree centigrade range, we see this kind of change. And what's this? This is about 12 to 14,000 years ago, maybe. Anybody? Ice Age. Okay, and so that's really, it's part of the Milankovitch cycles, right? The end of this last down drop and up, that's part of this Milankovitch cycle. And you can see we came out of the last ice age about here and have been relatively warmer since. If we look then at the last 1,000 years of that 50,000 years, across just a 1 degree centigrade scale, we see much smaller changes in that last 1,000 years. Due to all sorts of different factors, some volcanic eruptions, and various other things that at a much smaller scale can affect the Earth's average temperature. We can refer to all of these different things as different kinds of natural forcing factors, and that becomes important to understand this graph. So back in the late 80s, the United Nations pulled together an international team of scientists referred to as the Intergovernmental Panel on Climate Change, to start doing analyses of what do we really know about climate change, because concerns were starting to rise about all this climate change. And back in 1991, they first concluded that they had enough data to say conclusively that Earth's average temperature has risen. I don't know if you all remember that. But then in 1992, they did this kind of an analysis and concluded that not only is climate changing, but that climate change is due to human activities. And the way this analysis works is this. In both of these graphs, the black line is the actual temperature record from 1900 up to, I think it was about 2005 or 2006 in this case. And then what the red lines in the upper graph is the output of a model. They tried to model all this temperature change, putting in all the variables that they knew to affect temperature into the model, in the right strengths for each variable and all those kinds of details. And then they ran the model to see if the model was actually good enough to predict what we already knew to have happened. That's one way you test your model to see if it's any good. And they, based on these outputs, they said, yeah, this model's probably about as good a model as we can put together, because it predicted the past pretty successfully. And that had all of the human-caused or anthropogenic forcing factors of rising greenhouse gases and changes in reflectivity of the Earth's surface and various things like that, and all those natural forcing factors that we were just talking about. Then they ran the model again, taking all the human forcing factors out, okay? And saw what does the model say without the human forcing factors in it. And it says this. It says that across this time period, we would not have seen the rise that we saw. In fact, the Earth's temperature would have stayed pretty steady or maybe even declined slightly. I don't know if that's really a decline or not, but we certainly would not have been seeing this. And it's based on this kind of analysis. There are lots of analyses that go into this, but this is really the smoking gun. This is what told us in 1992 that yes, current climate change is caused by human activities, period. Not any of those natural forcing factors, because they would be doing this. Okay? And since that time, if you've heard other kinds of opinions on this, they have not been in keeping with what the scientific community has concluded. And they're likely simply political. Okay, everybody follow the reasoning that went into this. And this is the 2007 version of that 1992 analysis. They had a better graphic, so I chose that one. Yes, Carrie.
So I guess the reason that this is so important is the reason that we find out the reason for the cause of it is to figure out how to come up with solutions.
Yes.
Okay.
Yeah, and it's not about blaming ourselves per se. It's just about understanding why is this happening so that we can then begin to address how do we fix the why is this happening. And some other natural forcing factors were some major volcanic eruptions. Volcanic eruptions throw a lot of dust and aerosols into the upper atmosphere, which block incoming solar radiation, which can affect Earth's average temperature, and you can see that for some of these major eruptions. So in the short term, over a few years, those volcanic eruptions can reduce Earth's average temperature, but they're also putting CO2 into the atmosphere. So over the longer period, they're really increasing Earth's average temperature. So it has a somewhat complicated effect. Okay, and here's a record. Each turn around the circle here is a year. You can see the months from 1850 through 2016. It's a good way to kind of get a visual of what's been going on. And you can see two things here. You can see, for one, that the Earth's average temperature has been steadily increasing. And you can also see that the rate of increase has been speeding up across that time period as well. Okay. You can see lots of these kinds of projections for the Earth's temperature, the actual records, and then projections into the future based on either higher emission scenarios or reduced emissions scenarios. This is what we put together for Flagstaff when we were doing the Flagstaff Climate Action and Adaptation Plan over the last 2.5 years. CLIMAS, which is a research group down at the University of Arizona, made these projections for Flagstaff specifically. And so you can see that we've had a rising temperature already. And in the case of Flagstaff, it's largely been, not that our highs have gotten so much more extreme, but we've lost our lows. And that's what's driven the average up. And that's one of the issues in terms of keeping snow on the mountain. We can make snow till we're blue in the face, but if the temperature is too warm, it just won't stay there. And then predictions for precipitation, they're much harder. The predictions about average global temperature change are easy because we've seen such a steady rise in average global temperature. For precipitation, for a number of reasons that we'll talk about in a minute, it's much harder to predict and know what to expect. For one thing, warm air holds more water than cold air, right? And we're putting more energy into our atmosphere. So this particular projection suggests that average precipitation shouldn't change much by the year 2100. But one thing to notice is that, if you will, the variation across that average is really the fuzziness of that caterpillar, if you will. And all of these predictions for the future suggest that the caterpillar will get fuzzier. We expect more variation in the future in precipitation, more extreme variation. Okay, so now that your uncle, neighbor Bob knows that climate is changing and that it's caused by us, how can you help him understand what are the consequences of this? And he doesn't look quite convinced yet. And it's not just him, though, of course. It's them. It's everybody. How do you convince them? And I think the answer to this question is complicated, but really it's about understanding the person you're talking to, knowing the values and the language that they use when they talk about these issues, and connecting to them in one way or another. So as you all go out as emissaries to share this with the folks you know, family, friends, relations, Bobs, think about each one and what do they think about on a daily basis, and how can you connect to what they think about? So in a nutshell, what are we doing to climate change? Well, we're adding heat energy to the atmosphere and to the oceans, right? And what does that heat energy do? It's what drives weather. It's what drives climate. And so basically, as we're adding more heat energy to the oceans and the atmosphere, we're giving, I don't know if y'all see them, this is probably the most commonly used picture of the Earth from space. Y'all have probably seen it before, but you might not recognize it just because you haven't been introduced to Old Man Wind. And there he is, eyeball, nose, howling beard, wisp of hair. Okay, we're giving Old Man Wind that much more energy to howl up a storm. And what can we expect? We expect more extremes. This has been difficult in the communications about climate change for a long time. We used to say global warming, and then we'd have a cold snap, and people would say, what are you talking about? So we started calling it climate change instead to help people understand it more in this term that we expect more extremes. Some people are now not even saying climate change anymore, they're saying global weirding. To really emphasize that what we're expecting is new patterns and more extremes. I'm still using climate change though. Okay, and in fact, that's what we're seeing. Wow. Well, we went through this much more slowly than we used to, but okay. This is data from Deutsche Welle, which is a news source that I'd like to use. They're an international news agency out of Germany, and they tend to get much more directly to the point and have a little bit less drama. But if you look at the number of floods, and this is just number of events, so number of floods, number of storms, number of droughts, they've all been increasing as you might expect if you're putting more energy into the global weather and climate systems. The only reason the numbers for droughts isn't going up in the same way is just how do you count a drought? If there's a drought, it's affecting a huge region and it still just counts as one. Storms tend to occur on a smaller geographic scale, but if we counted them on the same geographic scale, let's say in terms of number of acres affected or something, these would all be corresponding to one another. Okay, and so I think you all have a sense from changes in the headlines that these things have been happening, but let's look at a few of these. Well, and overall, before we get into those examples, the changes that we're seeing to our life support systems are rising storm frequency and power, losses of water availability and increases in fire, latitudinal and escalator effects, and that has to do with how species are being affected by this, and we'll talk about that in a little more detail. Changes in productivity and resilience of ecosystems. We're also seeing ocean warming and ocean acidification. How does that work? Why is ocean's acidity affected by changes in CO2 concentration? Anybody?
I was wondering if you could explain why the drought graphic, I did not understand what you said about why the drought graphic does not match the others.
Well, if you think about, and this is a very general answer, but if you think about how a drought occurs, it's usually not just affecting a county or a state, it's usually affecting a larger region, right? And it still just counts as one drought. So we're getting more frequent droughts, but that doesn't show up so well here because we're not really counting the acreage. We're counting the just number of events. But if we did it in terms of acreage, it would be rising as fast as it is for storms and floods. That's all I was trying to say. Does that make more sense? Okay. So ocean acidification, it turns out that CO2 is soluble in water. And so the Earth's oceans absorb about 30 million tons of CO2 every day. And if it weren't for that, then the change in the greenhouse effect that we'd be seeing would be much stronger. The problem is, so that's a good thing, but the problem is that when CO2 dissolves in water, it forms more bicarbonate, which basically changes the acidity, increases the acidity or lowers the pH of that water. And as we're acidifying the oceans, and I won't probably show you the data on this because we don't have time, but we've been measuring the changes in the acidity of the oceans. It's already affecting the productivity of phytoplankton out in the open ocean. And phytoplankton are the source of about 40% of the oxygen in our atmosphere. So this is not a good thing. We want to reverse as quickly as we can that ocean acidification, let alone the ocean warming, which is bleaching the corals and doing a number of other things. And then there are a variety of direct human impacts, including the spread of human diseases and other things that are also a consequence of changing average temperatures. Okay, so for storms, yeah, I'm sure y'all remember Hurricane Katrina back in 2005, displaced over 400,000 folks, killed almost 2,000, and cost about $161 billion. You can see from the graphs that all tropical storms, all hurricanes, major hurricanes, depending on how you count it, they're all increasing. Named storms have been increasing particularly dramatically. So we're seeing more and more of these kinds of storms, and this is just about the frequency, but there's also been an increase in the intensity of these storms at the same time. Y'all remember Sandy, 2012? Killed fewer folks, but displaced 750,000 folks and cost $71 billion. Harvey, 2017, displaced over 30,000, killed 107, and cost $125 billion. Maria, also 2017, killed over 3,000 folks, displaced over 130,000, and cost about $90 billion. You know, we're seeing just more and more of these kinds of storms, and the price tag keeps going up, in part because they're more frequent and they're more intense, but also in part because we've got that much more infrastructure out there to be destroyed. Carrie. You know, I used to always say this was taxpayers, but it's not, and it's largely taxpayers, but not all of it is taxpayers. You know, some private homeowners are paying this price, and insurance agencies are paying this price. So it's distributed a little bit, but a bunch of it is paid by U.S. taxpayers. So this affects us all directly, yes. I haven't. Yes, the question is about rising sea levels. I haven't talked about that. As you warm the oceans, of course, that water expands a little bit, and that's causing rising sea levels. But also, we're melting the glaciers all over the world, and that's also rising the sea level. It's enough to where it's along coastlines. It is already affecting real estate values. So in Miami, for instance, real estate right on the coast, real estate values have dropped by 7%. There are projections about how people will be fleeing the coastlines of the United States and where they're probably going to end up, but we'll talk about that in the climate refugees presentation a little bit more. Okay, these are FEMA relief applications from folks who were fleeing Puerto Rico as a result of Hurricane Maria. So you can see that these climate refugees showed up in the lower 48. And this is another example of climate refugees. Some of them here in Arizona as well. And I know in Flagstaff we have folks who moved there when they fled Katrina, and they're still with us. This is just a map of distribution of climate-related disasters of one sort or another from 2002 through 2017. I'm not sure they accurately reflect all of the damage from wildfires, but they have a lot of the storm-related damage, not just hurricanes, but also increased frequency of tornadoes. In 2017, those costs went over $300 billion in the United States alone. And you know, some of them were major storms, but also wildfires caused significant amounts of damage. Here's the data for tornadoes, 1950 through 2016. And you can see that in the United States, the frequency of tornadoes has been increasing steadily across that time period. And the intensity as well. I don't have a graph to show you, but how many of y'all remember Joplin, Missouri? Okay. So we've had larger and larger tornadoes. That's the one that really kind of hit home for me, where they were talking about a swath for a tornado that was over a mile wide. I grew up in part in southern Minnesota, where we'd have tornadoes. We lived right on the lake, and for whatever reason, tornadoes lift over lakes, so we never got hit directly, but the swath was, a few blocks wide or never as much as a mile. This was taking out not just wooden structures, but cinder block schools. Okay. As I was saying again, precipitation is that much harder to predict, but the fuzziness of the caterpillar is projected to increase. That is the amount of variation in that precipitation. And these are projections for California and the Great Basin. And you can see the overall average doesn't really change that much, but the expected variation is much higher. And that's really what all of the different models predict, is increased variability in precipitation. And just a case in point, how many of y'all were familiar with the 4 to 5 year drought that California went through? This is what Lake Oroville looked like in California, August of 2015. It's a reservoir dam. There's the dam, reservoir lake. There's the dam down there. So we're looking down lake towards the dam. But if y'all remember, just 14 months later, it looked like this. This is looking upstream from the dam. So over a very short period of time, they went from drought to way excessive precipitation, where dams were overflowing, and in this case they had an issue with their spillway, and it started to undercut, and they were worried that the whole dam would breach as a result of this, and they started evacuating folks. I think they evacuated over 200,000 folks because they were anticipating that this dam was about to go. And these are just the depths of water that would have occurred downstream from the dam, and all the various communities and where they were located relative to the expected flooding. Fortunately, it did not breach, but we can expect more of these kinds of exciting moments with greater variability in precipitation.
That's depth in feet?
It's depth in meters.
Meters.
Yeah, Lake Oroville is a big, big lake.
You haven't mentioned anything about the Great Lakes or some of the major rivers in our country and around the world. How is that going to be affected?
Well, so yeah, in the West, we're a little bit less flood prone than the Midwest and the whole Mississippi corridor and other parts of the United States. In the final presentation, I do have some maps of the anticipated increase in flooding in those parts of the United States and in other parts of the world. I don't have those built into this, but we do anticipate that there will be higher flood risk with that greater variability in precipitation. And these are projections for the entire Southwest from Seeger et al. 2007 up through 2100. And you can see that we're expecting, at least according to some of these models, an overall decrease in the amount of precipitation. And some of that we're already seeing. We've seen issues with the flow of the Colorado River, which is fed by all of these western drainage basins. And so we're seeing less water in Lake Mead and Lake Powell, in part because we're using a lot of that water, but also in part because it's being replenished at a slower and slower rate, and a more, really primarily a more variable rate. As a result of drying out and warming, the West has seen an increase in numbers of fires and in an increase in frequency of large fires. So all these brown spots are areas that have burned between 1984 and 2010 in fires greater than 1,000 acres in size. And if we increase by another 1 degree centigrade or 1.8 degrees Fahrenheit, the fires are projected to increase by another 380% in Arizona and New Mexico. This is just a plot of... Yes, question.
Is there anything that can be done about those fires with the increase? I mean, we're projecting major increases, 4 times as much. Is there anything the Forest Service, anybody else can do to try to lessen the opportunity of losing another San Bernardino?
Yeah, a very good question. And if you're looking at this from a Forest Service perspective, this is all happening over decades of decreasing budgets for the Forest Service. So the main thing that you can do, really, since you can't change the rainfall, and go out and do a rain dance, but you can't really affect that. And so what you can do is do forest thinning. And for some forests, that really gets them back to their more natural state. It's different for different forests, but for ponderosa pine forest, for sure, the natural state is to have a much lower density of larger trees, which can withstand brush fires that then keep it from becoming a crown fire that takes out the whole forest. So that research comes out of Northern Arizona University, that we've been pushing for that for many, many years. Many forests are trying to implement it, but it's expensive also. We need to be increasing rather than decreasing the budgets for the Forest Service. Yes, question?
Lived here since 1976, and the Forest Service people just basically told us, you're in a burn area now. Afford to keep that we keep at the airport any longer. I used to go into the forest, and the tanker was called immediately by the guy that was in the tower, and he just told us, we don't have the budget anymore. That's it. It's going to burn.
Yeah. So, it's hard to answer that question when much of the country is in a mood of pay as little taxes as possible, reduce, this impact on my budget. But society is built on collective actions that we all collectively pay for, and if we want a better society and a safer place to live and all these different things, better schools, we need to pay for them, and we need to get our heads around that and just do it, I think. That's a personal opinion, no data.
But there's also a judge who declared that we should save the spotted owl and stop burning in our forest, and that's flying in the face of what the Forest Service wants to do. So there's judicial actions that aren't helping our cause exactly. Now, you might help the spotted owl, but Prescott might burn down. I mean, it's throughout New Mexico, Arizona, and Utah, I believe. So there's those issues that aren't helping.
Well, so there are a lot of competing pressures, and saving biological diversity is also an important thing. In the long-term survival of our species. We depend on all of those species. I'm not going to make a solid argument for that in this presentation, but we'll touch on it a little bit if we get there. All of those species out there are the nuts and bolts of our life support system. Every species contributes to the productivity and resilience of natural ecosystems. As we're going into climate change right now, we need as much of that biological diversity on the way in as possible if we hope to have functioning ecosystems coming out at the other end. And that's just kind of putting the whole thing into a nutshell, but I'd be happy to talk with you more as we go forward. But there are competing interests, no question. As human populations grow and pressures on natural systems continue to increase, we will see more and more such critical balance kinds of questions. But in keeping with what we've been talking about with the Forest Service, I don't know if you'll remember back in 2015, but we were running out of fire crews. We didn't have enough folks to go out and fight the fires. This is where I went to high school and junior high. Bishop, California. Anybody know that place? The forest there is Inyo National Forest, and when I was growing up, it was known as the asbestos forest because it never burned in a fire greater than like an acre. A lot of it is pinon juniper. Fires just didn't have the ability to grow. But this was in 2015, and things were dry enough, this was during that California drought, that major fires started erupting. So this is just north and west of Bishop in what we call Round Valley. Yeah, before Mammoth. Before Sherwin Grade. So it's right before you go up Sherwin Grade towards Mammoth. Before you get to Convict Lake. So Convict Lake is at the top of Sherwin Grade, but this is at the bottom of Sherwin Grade. And then the mountain behind it is actually Wheeler Crest. So yeah, we'd never seen these kinds of fires, and now we're seeing them. And you know, the headlines today are that. I just watched a video last night of the Paradise fire, and that was an incredible thing. And we're seeing more and more and more of those kinds of things. This was ours in Flagstaff a few years ago. This last summer we had the museum fire, which did not get nearly as large, fortunately. I was out of state at the time that this was taking place, so we were frantically looking at the internet which side of town is burning, and we were very lucky that it wasn't our side of town, but others were not as lucky. Of course, fire has all kinds of effects. It removes vegetation from large sections of landscape, which then leads to erosion, which further degrades the overall forest ecosystem. Downstream, that can lead to pretty significant erosion. In the case of this particular gully, a young lady lost her life there. She misjudged the depth of the water, got sucked in and stuck in a culvert and drowned. And that kind of flooding then leads to all kinds of other damage. So we lost over 15,000 acres. The firefighting costs themselves were $9.5 million. Flood and restoration costs over $130 million. 38 homes were destroyed and countless others damaged. And the revegetation efforts continue through today. So, you know, for my students, I think, well, is vegetation important to a watershed? Yes, it is. We don't often think of things that way, but it's very, very important. Okay, how are some of those species that are our life support systems being affected by climate change? Well, one of the things that we've identified is what we refer to as the escalator effect. How many of you have seen these kinds of diagrams of life zones on mountains? I don't know if you know, but the life zones of the world were defined by a fellow whose name was C. Hart Merriam back in 1898. He defined the life zones of the world based on vegetation surveys from the top of our San Francisco peaks down to the bottom of the Grand Canyon. And that's one of the reasons we call ourselves the Merriam-Powell Center for Environmental Research is after him. And in these life zones, you know, the different species that live in this life zone are different than this and this and this, because at the bottom of the mountain, the temperatures are higher, precipitation is lower. As you go up the mountain, the temperatures come down, and precipitation rises because there's more rainfall as air masses are pushed up over a mountain. And they cool adiabatically and can't hold their moisture. Anyway, so for those reasons of temperature and rainfall, you get different species that are adapted to each of the different conditions as you go up the mountain. What we've been seeing, and this is a study that reached the newspapers in 2013, done by a group down at the University of Arizona, where they had noticed that grasses of all sorts of different species had been moving up the mountainside as a result of changing temperature. And how would they know? Whether they didn't sit out there on the mountainside for years watching the grasses move, how would they know that the grasses are moving up the mountain? Well, then you can watch the animals move, but what are the old records? If you go to a museum of natural history, that's where they keep those records. They've collected specimens from each species and where they were located, where they collected each one back into the 1800s. And so we can look at the old records of where species were, compare it to where the species are today. And so that's where those kinds of collections and that data can really help us understand what climate change is doing. And we have lots of studies that are still looking at species across these different life zones and how they're affected by climate change down at Northern Arizona University. But of course, it's not just the escalator effect. On a mountainside, it's relatively easy to stay within your temperature range. You only have to go a few hundred or maybe 1,000 meters, and you're still in your temperature range. But if you're in a flatter landscape of some sort, you might have to go a few hundred kilometers or 1,000 kilometers to stay within your temperature zone. And we're seeing that as well. We're seeing a northward push for many species as climate changes. And these are all species that have been affected by the escalator effect. in one way or another. Edith's checker spot tends to pollinate wildflowers that are up on top of mountain ranges. As those wildflowers get pushed upward and outside of the range of temperatures they can handle, they get pushed off the top of the mountain. They go locally extinct, and Edith's checker spot goes locally extinct as well because it depends on those wildflowers. In some cases, the stories are a little bit more complex. Like for the scarlet Hawaiian honeycreeper, they're being pushed up the sides of the mountains of the Hawaiian Islands by temperature. But the reason is that as the temperatures rise, mosquitoes, which have all these alien diseases, bird diseases, are going higher up the mountainside, and it's those diseases that are actually killing the birds, and so the birds have to go higher to stay out of the range of the mosquitoes. So in some cases the stories are more complicated, but they're all being pushed up the mountainside. How many of y'all know pikas? Pikas. They're about this big. They look like little mice, right? But they're actually not mice at all. Anybody know what these guys are? They're adorable, yes. They're actually little rabbits. They're little relatives of rabbits. And you can see it. If you know that, you can kind of see it in their face. You know, the ears aren't as long, but they've got a rabbit face for sure. And they're little hay farmers. So they live in the scree piles up way on the top of the mountain. They run out from the boulders and collect vegetation. They lay it out on the rocks to dry, and then they take it under the rocks in these hay piles that they use for food and for insulation over the winter. So they really are hay farmers. They're nature's hay farmers. But they're very temperature sensitive, so 80 degrees Fahrenheit is lethal to them. And so as things get warmer, they're being pushed, like we said, off the top of the mountain. They can go higher only up to a certain point, and then they go locally extinct. These are projections for future extinction on different mountaintops based on different emissions scenarios. If we have higher emissions, then they get pushed off of more areas. And if there are lower emissions, then the climate change isn't quite to the same extent. How many of y'all are familiar with the National Audubon Society? They're a large group in the United States, a large group of bird watchers. And what they do is they have this, what they call a Christmas bird count, where they all go out and do transects and count birds in a systematic way. And all of that data from bird watchers across the United States goes into a large data set. And they've been doing this for many years. So back for the observations of different species in 1966, 67, they took all those observations, you know, how many were here and how many were here and where they all were, and they kind of calculated what you might call the center of gravity of observations for each species. And so the light blue dot is the center of gravity of observations for the pine siskin in 66, 67, and the dark blue dot is the same thing calculated for observations made in 2005, 2006. And you can see that different birds have shifted in different ways. Some more east, some more west, but all of them have shifted north. So there's like the grass study on mountains. We have this record, we can make comparisons, we know all of these species are already moving north. How many of y'all know what a coati is? Coatimundi. Well, they're showing up in Flagstaff more and more. And here, well, that's interesting. So their normal range is Central America and, you know, maybe into southern Arizona a little bit. But they've been moving northward for the same set of reasons. They don't normally co-occur with ponderosa pine trees at all, but this is what my neighbor took a picture of in 2015. An impressive critter, a very large coati, who had been chased up a tree by a bunch of the neighborhood dogs. They normally eat fruit, rotting fruit and that kind of thing, so they're way outside of their natural habitat. I've seen them myself up on top of the rim out at Walnut Canyon, so they are coming up further and further north. We're seeing more javelina and more roadrunners in Flagstaff as well. Okay, so we're affecting our natural ecosystems in a variety of ways. We're already going through a global mass extinction due to habitat destruction and a variety and pollution and other things. And now this is being exacerbated further by climate change. As we push species into new habitats, well, you know, so these birds might be able to move, but what if the insects or the plants that they depend on don't move as fast as the birds can? So we're reshuffling ecological communities and thereby threatening the continued existence because we're breaking up ecological relationships between species when we do that. Okay, agricultural productivity. These are projections back from, I think, 2009 from the United Nations Environment Program on projected changes in agricultural productivity by 2080 due to climate change. And you can see that a lot of parts of the world are expected to see drops in agricultural productivity as a result of climate change. Some areas are expected to see increases. Parts of the United States are expected to see increases, and significant parts are expected to see decreases in agricultural productivity. In a country like ours, we've got a lot of economic stability and infrastructure where we can deal with these kinds of changes more readily. Other parts of the world which are already stressed for many different reasons can expect to be further stressed by these kinds of changes. How much yield of a crop on a particular patch of land. So agricultural productivity expected to go down. Now, there are lots of different ways that farmers can deal with these sorts of changes. So one thing, they can plant different varieties of the crop that they plant that are more heat adapted or drought adapted, and they're already doing that. In the extreme, they can shift to new kinds of crops, and we'll talk about some examples of that in just a minute, I think we'll get to it. Oh, maybe not. Okay, so in that context, we want to talk about drought a little bit. What is drought? Drought is kind of a loose term. It's a relative term. Well, it's drier than it used to be. The crops didn't produce as much, so we call it drought. But overall, if you look at the effects on precipitation in the United States, all of these green areas are areas that have seen increases in precipitation, and this is relative to the averages of 1951 to 2001, the period of 2003 to 2007, saw increases in precipitation here and decreases in places like this. Overall, if you look at the data, we've seen about a 5% increase in precipitation in the United States as a result of climate change. But back in 2007, southern Minnesota had seen an increase in precipitation. And yet, at that same time, corn farmers in Minnesota were experiencing drought. How is that possible? Increase in precipitation, yet they're still experiencing drought. And it was very real. I mean, I don't know if you remember the headlines, but there were pictures like this showing what Minnesota farmers were dealing with. But they'd seen an overall increase in precipitation. Why this? So the changing in the timing of the rainfall can have this kind of an effect. In this case, it wasn't that, though. It wasn't this relative snow and rain ratio. And runoff can lose the water, but... So we've seen this increase in precipitation, but what else have we seen? We've seen this. We've seen an increase in temperature. So what happens to water availability when the temperature's higher? More of it evaporates, less of it's available for plant growth. That's the bottom line, kind of. So they were experiencing drought in spite of the fact that they had seen an increase in rainfall. And to deal with that, long ago we devised the Palmer Drought Severity Index, which takes precipitation and temperature and wind and soil characteristics into consideration. That's the actual formula. We won't go into it.
Is this going to be on the test?
But you got to realize that even if we get a slight increase in precipitation, the temperature might evaporate to that effect, as it were. And I think I'll end on this slide. We're seeing that kind of thing here. Last spring, I put together this thing up in Flagstaff called Climate Elders Tell Stories of Change. And we had a number of different elders who were telling their change experiences. And one of them was Jim Babbitt from the Babbitt ranching family. They, since the late 1800s, have been ranchers in northern Arizona. And he went out and talked to his cowboys and range managers and folks and said, you know, what changes have you all seen? And they told him, well, we've always had spring wind. Now we have fall wind that's just as strong. And that's something we hadn't seen in the past. And as a result of that, the range is drying up. We need to haul more water. We need to haul more feed. And so it's affecting our bottom line in a pretty big way. And then after those stories, I got this data from Eric Burden. And what they're showing is all of these red areas are areas that have seen greater than 80% reduction in the productivity of the range plants, grasses and shrubs. And so it's not surprising that these data are saying this and that the cowboys are saying, yeah, we've got to haul more water and more feed. So this is a different kind of agriculture than we've been talking about in the others, but it's still affecting us locally. And the ranchers are experiencing it. Yes, question?
Are worldwide statistics as comprehensively collected and known as they are in our country?
I'm not sure if we've got quite as much detail, but there's other parts of the world that have more detail than we do too. You know, places like Great Britain and much of Europe. And the United Nations has been collecting this kind of data on a global basis. So we have pretty good data sets globally. When we do put the climate refugees presentation on for Prescott, we'll get into the Syrian war. And I don't know if you all have thought about the Syrian war being the result of climate change related drought, but really that was the trigger there. Just to put it all in perspective. And we'll talk about the details then. So there's a lot more we could talk about in terms of the effects of climate change, but we should probably leave it there so that we don't bump into the next event. So thank you all for coming. And I want you all to be emissaries, right? So if anybody wants a copy of this presentation, please bring your data stick, your little flash drive thing up, and I'll be happy to send a copy home with you. They're too big to email, or I'd email them to everybody. But if you want a copy, please bring your data stick up, and I'll be happy to give you one.
Hold on one second. I'm sorry. I didn't mean to interrupt, but I know we're all about the pie right now, so I'm panicking a little bit. I want everybody to know that Professor Samar has started in October quite a tour of duty on behalf of Yavapai College in Ollie. This is his 9th, I believe, or 10th in this month alone in Sedona, Clarkdale, and here. And he's also a professor at NAU. So, I mean, he is just really doing so much for our organization. He's also a board member for Northern Arizona Climate Change Alliance. And I just want to give him a special thanks for all of his hard work as a volunteer providing this information. And my volunteers are rushing to the table to catch you in case you need our upcoming events and you want to sign up. But Professor Samar will be back November 16th for a presentation at the library, so grab a flyer on your way out. And here's Tricia, who wants to make an announcement.
I'm going to tell Rudy.
Oh, no, I thought you were going to say something.
Thank you all for being here. Thanks very much to the social committee for sharing this space so that all of you would fit in the room. So thank you, social. Woo! And we're going to shift into a much lighter topic of pie and popcorn and Halloween costumes for those of you who participated. Good job. Thank you all for being here. I will get information about their next talks. I will talk about the capacity of the rooms for their next talks, and I will include it in my announcements. So open your emails from my announcements and look for those next talks. So thank you, guys.